the scientific community and the Fab Labs that certainly have a lot to learn from each other, and to invite you to, as it was already mentioned, to develop the bridges between the Fab Lab community and the scientific community by proposing sessions for ESOF 2018 that would be common to Fab 14, so that we can make smooth bridges between the two communities. I would like to thank, of course, the Fab Lab for hosting us, the ESOF organization, Aerospace Valley, and ONERA, and all the speakers of this morning who have taken a lot of time to prepare very good presentations. Thomas Peruz, who's the robotics expert and artist who presented in the morning, and the scientific committee, Rachid Alami and Michel Devy from LAS CNRS, and Catherine Tessier from ONERA. So I now call Henri de Plinval. Henri de Plinval is the program director for drones with ONERA, the French Aerospace Research Center.
Good morning, everyone. Do you hear me well? It's okay? Very good. So I'm going to, let's say, introduce this session dedicated to cooperation between robots and humans by talking about, let's say, cooperation for heterogeneous robots. And by this big word, I'm simply mentioning different types or kinds of robots, namely ground robots, naval robots, and flying robots. And I should probably tell you right from the beginning that I have sort of a big bias towards flying machines. And this may be because I'm working at ONERA, as Dominique said. So very quick word about ONERA. ONERA is the French public research lab for the domains of aeronautics, space, and defense. Our mission is threefold, as you can see. We want to prepare the future science and technologies. We have to innovate to the final benefit of the industry. And finally, we have a mission to propose to offer a high-level expertise for the French state. This being said, let me maybe dig into my topic today, cooperation for heterogeneous robots. I'm going to be somehow fast because I believe that we are a little bit late, but I'm going to give you an overview of this topic, and I think my colleagues after me will build on other aspects of this very big topic. So I'm going to first introduce this topic by mentioning some kinds of applications that you can find. There are many of them, but I'm just going to give you a glimpses to it, and then I'm going to give you ideas about some of the main technical challenges that one is facing when dealing with actual cooperation between different kinds of robots. So since I believe you audience are quite diverse in terms of knowledge with respect to the domain, I'm going to give you somehow some glimpses or ideas about this. No equation in this. Okay. So let me first start with some application. Again, there are so many applications for cooperation between different kinds of robots, but I'm just going to mention some of them. Civilian applications, of course, are so many. You have very important applications related to crisis situations, like in terms of problems happening in industry sites or these kind of things, or nuclear incidents, where a team of robots, namely ground robots and flying robots, maybe naval one, as you can see on the picture to the top right, can help provide a very good situational awareness of what is actually happening on this crisis situation. You have important application related to what I would call post-earthquake situations, where in a village, for instance, you have an earthquake and you have destroyed buildings, as you can see to the bottom left part of the picture. And then you want to send, again, a team of robots, so maybe a fleet of flying drones inside these buildings to find people who may be stuck inside these buildings. And to do this, again, cooperation is a high benefit for that. Then you have other type of application related to meteorology. We have projects dedicated to that. You can see the picture to the right, dedicated to sending a fleet of drones flying around clouds to make scientific measurements in order to better understand the climate, the weather, or maybe make weather forecasts, improve the weather forecast capability. Then you have, of course, very famous, I would say, application cases related to loads transportations, small loads in particular, with the, let's say, Amazon, Google scenario, which you may have heard about, carrying small, loads inside, for instance, in urban environments. And of course, you can imagine a lot of drones doing this all together to be more efficient. UTM, sorry, it's an acronym. It stands for Unmanned Aerial System, so drones, traffic management. And it is the name NASA gave to the big program dedicated to thinking about the way we will manage tomorrow the sky with all these UAVs or drones flying all around. And then, of course, you have also defense applications, of course. So you can have, for instance, broad surveillance applications, which is not only important for defense, but also for civilian applications. And also find people in a village. You have the picture of a village to the right side. And there are other kind of applications. And this is somehow related to what Thomas Perrus did this morning. So I just leave it to you to see it. I hope the sound is okay. Okay, so apart from being a lot of fun, this video, which is not very new, by the way, was made at the University of Pennsylvania by the very famous team of Vijay Kumar a while ago. But apart from being fun, this video helps me introduce some important distinctions that I want to do right from the beginning. Some considerations, if you want. First of all, I want to distinguish between what I would call coordination and actual cooperation. Coordination is this, what you saw in the movie. That is, you ask each robot to do something on its side, okay? You want this one to do this, and because you ask the other one to do something else, all together, it does something nice. And it's already important and good, and it can help you do a lot of things. But you can understand right away that it's not the same thing as asking a fleet of robots to actually cooperate, to actually take care of what the other is doing, you know? You see what I mean? So this is an important first distinction. When you want to do cooperation, you want to ask what you actually want the robots to do. Another distinction, which can lead to hours of conversation, but I just want to give a glimpse at it, is automatic control versus what I would call autonomy. What I want to say here is that one thing is to have a drone or a robot accomplish a task, okay, automatically. But another thing is for this robot to be able to face unpredicted events, like breakings of its actuators or sensors failures and so on, and actually deal with these events and take decisions in the face of this dynamical changing environment. This is not the same thing again. Indoor versus outdoor. You saw the video was made indoor, and it's a very good and it's very nice, but you can understand right away that doing this indoor with possibly cooperative sensors helping you to locate the different robots is not the same as doing it outside with also the wind conditions and so on. And also the transition between outdoor and indoor. I was talking before about earthquake, exploration into a village, drones sort of going into houses and so on. When you have a transition between outdoor and indoor, this is also a very complex task, if you want. And then you have the individual autonomy, which is what I said before, the capability for one robot to face events and to behave in a good way and in a safe way. And you have the collective intelligence, that you want the fleet of robots to actually do something all together. And this is really not the same thing as we will see later on. And finally, this is the title of my talk. Another distinction is if you want to do a cooperation between a fleet of robots of the same type or heterogeneous robots. If you have this, again, the same example, a fleet of ground and flying robots getting into a village to explore it, you can take advantage of the different natures of the different robots. The ground one maybe will be able to get into a building very easily sometimes, but it can be stuck by an obstacle. And then it can call for a flying one to make a map so that it can find its way in between the obstacles. So this is sort of initial consideration that we will get into in the rest of the presentation. Coordination in a fleet, when you want to make a fleet of robots, and this is in particular true for flying ones, do something all together, you have first like basic challenges which are not so easy to deal with. First of all, you have automatic control issues. You want to make it automatic. You want to, I talked about that, reject the wind. The wind can be a very large challenge if you are flying outside. And I put here a picture of a computation made in a village to assess or to estimate the wind, the turbulences inside this village. And I dream, if you want, that in a near future, we will be able to have this on board the drone so that it can, based on what it measures from the wind and based on a map of the village, estimate what will be the turbulence behind the building. You see what I mean? And then define a trajectory which will take advantage of this knowledge to be more efficient. And also you have guidance issues, that is trajectory computing issues. And this is a bottom left picture. You want to, of course, compute a trajectory for the drone and the fleet of drones or the fleet of robots to reach its goal. But you want also to take into account some things like maybe the GPS localization will not be so good because I will be inside a building or next to a building. And so we're able to say, when I will reach this place, my localization will be less good, so that I will take more margin, safe margin with respect to this building because I know that I will not be very accurate in my positioning there. So you have these kind of issues. Another issue when you want to do coordination, you want to have this fleet of, for instance, flying robots, flying all together. You have relative positioning issues. How do you know your position and how do you know the positions of the other robots in the fleet? Do they cooperate by sending you a position? and what is the accuracy of this position. And then you have also other questions like how do you manage the shape of the formation? Do you want to have a master, which is one of the robots, which is a leader, and the other are slaves, they just follow it? But in this case, if the master has a problem, what do we do? How do we decide which one will become the next master and so on? So for instance, an idea that my colleague had for that is to use a virtual leader, which is not an actual robot, but which is, let's say, the average of the position, and this one will be controlled, so that even if we lose any of the drones, there is no problem. The virtual leader still exists, if you want, okay? And everybody is positioning itself with respect to this virtual leader. So this is just a small video to show you an example of one of the applications we worked on. We are actually working on now, which is a cooperation of flying robots with spread radars to detect other flying objects. And this is a very challenging and very, very nice application case where you have all these drones flying all together to detect, by cooperating really with each other, to detect other flying traffics. Then, as I said, when you want to go, let's say, one step further to get into these facing unpredicted events, you need to have, first of all, an individual robot intelligence, if you want. You need this robot to be able to face many different kind of events. At the top right of the slide, I showed an illustration of techniques that people are working on to be able to face sensors failures. For instance, your UAV, your drone, does not have any more measurements of its speed. Are we able, by computations and by the help of other sensors, to recover this missing information? So we're working on that. And the bottom left picture is an illustration of the 3D reconstructions that the robot is able to do inside an unknown building, thanks to, in this case, its onboard video cameras. So by making computations on the images taken during the flights, in flights, by the video camera, you can reconstruct, you can build in real time the 3D, if you want, a 3D map of the inside of this building. And you can, in this case, you can then compute trajectories inside to find the best way to find, for instance, lost people inside this building. Then the next step is the collective intelligence capability. This is a short video of an experiment we made with, I think there were 8 robots, ground and flying, and we even introduced virtual robots. That is, we had, as you can see, actual physical robots, ground and flying, but we had also virtual ones, which did not exist, but only in the computers. So we mixed real and virtual ones. And the important thing is we gave each of these robots with first an individual intelligence capability, as I explained before, but then also a collective intelligence, algorithms, software, and capability. And each robot has the capability to define the mission for the whole fleet, based on what it knows about the positions and capabilities of each of the robots in the fleet, so that we are, in particular, able to face the loss of some of the robots. So we simulated one of the drones being killed, if you want, and the rest of the fleet is able either to call for a spare, this is the easy way, or to reallocate, if you want, the mission, the global mission objective, into subtasks for each of the remaining robots. You see what I mean? So we are able to face unpredicted events not only at the individual level, but also at the fleet level, if you want. And this is a very important task to do. Another important thing is the communication between the different robots. If you are in particular exploring a village, you may face communication problems in between the different robots. So there are different ways to deal with that, and it's a big and complex problem. But one thing is you can add to the collective goal of the fleet an objective to maintain the communication network in between them. telecommunication issues. I was talking about that. You have also related to that another electromagnetic, if you want, issue, which is the GPS receivers inside urban environment can be very hard to get. And so this is a map that was built of the regions inside this village where the probability to lose the GPS signal is the highest. If you have this sort of map on board the robots, you can, again, compute a trajectory which will take that into account so that you go to the places where you know that probably you will get a good GPS reception. Another topic dealing with flying robots is, as I mentioned briefly before, the insertion into the airspace. You have so many flying things today in the air, and with the multiplication of drones, you may have much more. So we need to make new operational concepts to insert them inside this airspace and to take care about such issues like actuators braking. I was talking about that before. When a drone is facing a problem, you want, for instance, to make a bubble around it and to forbid any other aircraft to get inside this bubble. But then you want to see if this operational concept is possible. Meaning, if you have so many aircraft in the air, is it possible to save a bubble and to say nobody flies in there? Is it doable in terms of the size of the traffic? So this is a kind of question that needs to be asked. Finally, also very important topic that I believe my colleagues will dig into much more, the human-machine interaction. And I want to share only one thing with you about that. That is the supervision by one human being of an autonomous system. You know that the human brain is fantastic, of course. It has a lot of capabilities, but it has also some particular flaws that we need to know and to understand so as to design very dedicated and efficient interfaces between the human and the robots. And for instance, when a human being is supervising a kind of autonomous system, then at some point it will unplug. Unconsciously, it will think, the human being will think, this robot is able to do the job. I don't need to know anything. And so that the consciousness of the human being will be lower. And if there is a problem, and if he has to act to do something, it will be longer for him to get back to the job. So that we need to understand this kind of phenomena, understand how the brain behaves, so as to define, again, new interfaces, so as to keep the consciousness of the human supervisor, for instance. And finally, when dealing with all these aspects related to cooperation between different kind of robots, you always need simulation, very efficient simulation capabilities. And of course, everybody is doing simulation, but here I'm talking about very refined simulation capabilities where you are able to, for instance, to model very accurately the sensors, the response of the environment, and so on, and the behavior of the different dynamic vehicles. And also, you need also capabilities to model, as I said, the air traffic, to have a good idea of the air traffic in the air, the aircraft, the drones, and to see if your operational concepts are efficient or not. And with this, I am done. And if you have some questions, I will be happy to answer. Many colleagues at ONERA are involved in this kind of works. Thank you very much.
Thank you, Henri. Last chance for a few questions, if you have. You may ask questions in French. Vous pouvez poser des questions en français, nous pouvons traduire. Okay. So then I call Professor Alin Albu-Shäffer. Professor Alin Albu-Shäffer is the head of the Robotics and Mechatronics department of the DLR, the German Research Center for the Aerospace. and he's also professor at the Technical University of Munich. So he's now going to present a talk on robots in the factory. Thank you.
Yes. Good morning, everybody, and thank you for the invitation. It's great to be here. It's for the first time to attend the FabLab, so I'm really curious to see the exhibition afterwards. I will talk about designing and controlling robots for direct interaction with humans, and since the colleagues who organized that are coming from the aerospace area, I will focus on some aspects of aerospace, but mainly on space actually, but also look into very general applications of robotics, more from the mechatronic design and control point of view, but also some computer science aspects. And our motivation at DLR is to build robots which help astronauts in the work in orbit, but also for exploring and colonizing planets. And we hear more and more about serious plans of NASA and the international community to go to Mars. Elon Musk says 2025, NASA is more cautious and says beyond 2030, but I bet with everyone that before we will have humanoid robots there, before we will have astronauts there, we will have robots in different kinds and also humanoid robots to build habitats. Of course, the expectation of most of people related to robotics is determined by science fiction movies. And I like to show this movie here, I, Robot, because the people who did this movie did a very good research about capabilities of robots and about state of the art of robotics. And what would we expect from a robot which works together with us? First of all, to be safe. And these are all from the trailers of the first minutes of the movie. So to be safe, which is visualized by the interaction with the child. To do some work which people do not like to do, like waste disposal, maybe to help in the kitchen with some superhuman performance, or just being a butler in everyday life and doing some jobs other people would not like to do, or which would be just fancy to be done by robots, right? But when I look to that movie, and this is a scene coming later on where the robot gets consciousness and runs away from people which want to destroy him, the first thing I asked is, what would I put here? Because if you go out and look at the robots, if we have seen the robot before, the motors are still less powerful than human muscles are. So this is where we come from. We started building robots first, and then looking about control, and then interaction with humans. And then a very big question is, how do you program those robots? We hear the question here, it takes days, weeks to do a simple choreography. We would like to instruct them as humans instruct other humans. So, and then other issues of teleoperation and so on. And the closer the robots get to the humans, the more you can ask questions, scientific questions about how some functionalities work in humans, try to implement them in robots to validate and maybe get some new ideas, hypotheses for neuroscience and so on. There's some research also happening here in Toulouse. I know the work of Jean-Paul Le Mans. He's looking also into that, into the interplay between biomechanics and neuroscience. Robotics is still a pretty young discipline, about 50, maximally 60 years, depending where you start counting. And this is our history at DLR, and I started as a PhD student building robot arms, and this took years and years, but then, you know, after a while, 2003, we had a version which we licensed to industry, and now there are, well, several companies doing interactive robots. And those robots are modular. You can put them together with using the same modules and then build up more and more complex humanoids. And now the focus is also more and more on behavior. So Of course, it's a pretty slow progress compared to the expectation of science fiction movies. Well, but still, you know, compared to human evolution, maybe we are fast, depending on how you assess our results. Anyways, what do we mean by soft robotics? We have seen classically robots are programmed to follow trajectories. This is how robots in industry and manufacturing work today. But it's not the way human work. So if we want to grab an object, we don't say I move 30 centimeters from my base and 30.2 and 50 micrometers precision. But what humans do is they use vision, they use the sense of touch, they use force sensing to touch the table, slide along the table until they encounter the object and grasp. So it's everything sensor-based, and this is what we try to reproduce there. So the robots can program the stiffness, have some sensitivity in their joints, and most important of all, by having this kind of sensors, you can prove that they are safe. And this is a master and later on PhD student of mine who was the first to do this kind of experiments just to show that robots are indeed safe, that you can detect the collisions. He's a professor now, so he didn't get any damage. He's a full professor in Hanover and has also companies selling robots, right? How can we imagine controlling those robots in a different way than moving each joint one by one on trajectories? So when you are doing this kind of task, our approach is think about if you grasp an object, you just put springs between each finger and the middle of the object, some virtual springs basically, like in this sketch. Meaning that, you know, if the object is a little bit displaced, a bit bigger or smaller, then you won't have huge forces, but those springs will adapt. And then out of those virtual springs, you can compute the force of each individual motor. So that's the basic idea, and then, you know, as you have seen here, to grasp the balls, you can put some springs between the hands. To grasp on objects, you know, you can attach the springs to the fingers and so on. So it's a very basic principle, but it works well. And this is very in contrast to what I mentioned before, industrial robotics. If you go to any car manufacturer here in France, probably to Peugeot or Renault, that's the way they produce carrosseries today. There's no human in there because the robots are very big, very fast, but also very dangerous, right? And what we are looking at is a new type of robotics where the robots interact with the humans, right? But when we designed those lightweight robots, of course, the first thing was to certify them. So when we licensed the technology, we were asked, can you prove that the robot cannot hurt the human? You know about Asimov's laws, and well, the first law is the robot should not hurt the human under any circumstances. Can we guarantee that in a way, in a systematic way, car industry does testing? And we were the first to start doing this kind of tests with tests, crash test dummies, and you know, it took like 5-6 years until we developed our understanding about what could really happen, because there are many ways a robot can hurt a human. He can also, you know, have a sharp tool in his hand. He can block him at a wall. He can crush, hit, whatever if the software fails. So we rely on those sensors, some very different kind of sensors, and after years and years, I think we have a very clear methodology how you can assess and certify a robot to be safe for interaction with humans. And this also changed the regulations. Like 10 years ago, the industrial regulations prohibited shared space between humans and robots. And what happened now is that after the regulations have changed, after there are manufacturers which sell these robots for interaction, all big robot manufacturers, if you go to Hanover Fair, for example, in Germany, which was just 3 weeks ago, the main topic was human-robot collaboration, the main topic for automatization. So not anymore the big, very fast, precise robots, but robots which interact with the human such that you can combine, you know, the intelligence, the flexibility of humans with productivity of robots. And these robots still tended to be very expensive, about 90,000 euro. Now we have a spin-off company of exactly the PhD student I have shown before, who tries to sell those for 10,000 euro. And he tries also to develop app concepts. By the way, those robots, I mean, he demonstrated at the fair an application where those robots build other robots, right? At least in part, they do the assembly. So that's how he looks now, some years later, as a professor. And if this comes through, then I think we'll have a breakthrough in making robotics affordable also for small enterprises, also for small lot sizes, because the programming becomes much more easier. Okay, coming to the programming. Programming for interaction becomes much more difficult than standard programming because you always have a human in the loop. So you need to detect the human, and the robot needs to react to the human accordingly. So the human should be able to stop it at every time. We develop different ways of interaction, image processing, but also gestures. You can just touch the hand of the robot, and the robot will stop. You know, you can go anyways, always, and stop the robot. If you pull harder, then it will just float away. Then you can fix what you have to fix. Then you have another set of gestures to open the gripper, to close the gripper, then you confirm, and then the robot will continue. But designing this interaction is very difficult, and I think the big success of the smartphone is not because it's a great phone, but it's because it's such a great interface, because anyone can understand it within 20 minutes, and it's a pleasure to work with. So our question is, can you program robots in a similar way? Not in the way we are doing it today, in writing Python, C++, Java, whatever code, and needing computer science specialists, but just take the robot by the hand, show a position, maybe use an app to parameterize, and then make a framework in which a big community, similar to the way FabLab works, a big community develops specialized apps which are uploaded in the cloud and then can be shared. So this is the concept we are trying to follow in this direction. Now I would like to talk about another topic which you can do with interactive robots. In the case, you know, the tasks are very complex, the level of intelligence is not yet high enough, and this is teleoperation. It's another way of interaction between robots and humans. It's of having a robotic avatar, if you want, right? So you have the operator here, and he can stay anywhere in the world as soon as you have a teleoperation, an internet connection of about 100 to 200 milliseconds delay. He can see what the robot sees in 3D because the robot has stereo cameras. And he's commanding the robot using those input arms. The point is not only that the position is commanded to the robot, but when the robot touches something, it has force sensors, so the person can feel the interaction forces. So it's a level of immersivity where he feels like, being into that avatar. Of course, we know the movie Avatar, where everything is done by the brain interface. Our starting was with these robotic arm interfaces, and we use that in different applications. Of course, you can do that to do maintenance or repair in dangerous areas like Fukushima or earthquake area and so on. We started in space applications, and our motivation is, again, the first thing which will happen when the first mission will go to Mars is that the astronauts will stay in the orbit, will not land yet, because if you land, you need to land also a rocket to bring him back. The technology is not yet there. So probably the first mission, as it was in the 60s with the moon, will be that astronauts will orbit around Mars and place robots at different locations and then teleoperate them, like having avatars on the surface of Mars. So we try to develop this technology with many partners, with European Space Agency, ESA, with NASA, with Russian partners, and experiment them on the International Space Station. So playing that scenario, Earth instead of Mars, and the space station as an orbital spacecraft. And I will show some experiments we've done the last years. We tested different interfaces, exoskeletons you can carry around. This is a work of ESA. Input joysticks where you can have the force feedback, or even simple interfaces like a tablet PC. And these were first experiments we've done with the Russian colleagues and with this force feedback joystick. This is Sergei Kononenko, and he controlled from the ISS robots which were placed on ground, and they had a lot of tasks to experiment how telepresence, how force feedback feels in space. And then at the end, we did a public outreach demonstration, which was also on German TV, where we had the astronaut on the ISS, again, feeling the forces of interaction, and we had our humanoid robot on ground. And you not only could hear and see the astronaut, but you can also, feel, shake hands. He could do some tasks. Then he met his wife and his son. They came and said hello to him. I mean, he's there for half a year, up to 1 year. And then even he manipulated some objects as this ball, and he did it jointly. So some people manipulated one arm from St. Petersburg in Russia. The other arm was manipulated by the astronaut, and they just jointly performed some tasks. So the message is, you can operate, if you have a good radio or internet connection, a robot at any point in the world, as long as the time delay is below one second. The same concept of teleoperation and of interaction to a remote robot, we applied for surgical robots. There's actually only one manufacturer which sells surgical robots today. But in US, 80% of prostate cancer surgery is done by robotic systems. Why? Because actually the surgeon operates still, but he can do the motions in big, and the robot will do it in small. And we did the next step of teleoperation, so we have a robot doing the operation. Now you don't need to be scared and worried. This is just a joke movie which our co-workers did for our Christmas party. What in reality happens is that we have a teleoperator here. He operates the robot, and the robot plays the role of the surgeon and operates on the remote side. This is just to show that you have like 150 motors here inside. You have twice propagating a stereo image, twice propagating the forces, and the system still works. So, teleoperation is something which works really well. But yes, be assured, in reality, you will have a surgeon here and not a robot. This is just, just a Christmas movie some years ago already. Anyways, what's next? How does it continue? We have seen these robot arms as interfaces. Now people are looking more and more into natural interfaces about measuring currents of muscles and nerves. And of course, the electronics is still quite complex and bulky. Now we get rid of these cables. So I think in 2 or 3 weeks, I will get a video without the cables. But those natural interfaces use these telemanipulation concepts to either teleoperate robots by just contracting your own muscles or operate prosthetic devices. So this is a PhD. He has, of course, or a postdoc actually. He's a healthy person, but he demonstrates how he can operate a prosthetic hand. And we have a lot of tests with currently we have 2 patients. One is coming from Iraq, he's an Iraqi amputee, and one is a German person which by birth has degeneration, so he has no hands. And we test how many of the activities of daily life they can perform using this prosthetic hand and a very natural interface. And the difference is today prosthetics, they just have 2 fingers and they can open and close. While these new devices, they have 5 fingers, and they can also control the forces of those fingers. So they can control how strongly they press on a button, for example, or how strongly they grasp an egg. And what's the next step? Well, we had also some experiments with a team of US scientists from Brown University using brain interfaces. This is the upper image. And these brain interfaces are not allowed yet, do not have medical approval in Europe, but in US they are. And this person, she's a paralyzed person. So she was paralyzed for 15 years, but she had this brain implant in the motor cortex. And when she imagines that she would like to move her arm, the signals are still in the brain. So if you have electrodes which record those signals, and then you use machine learning techniques to transform those signals into robot motion. And we were addressed by the Americans because of this, safe, compliant, reliable robot. Then you can transmit those signals to the robot, and she was for the first time able to grasp a bottle, bring the bottle to her mouth and drink. So she can really move only her head. right? And this was great. Still is preliminary. Still there is our PhD student in the back paying attention that nothing bad happens, right? He has a big red button where he needs to press if something goes wrong. But it shows that this is feasible. In Europe, these brain interfaces are not allowed. So what we are doing this using these electromagnetic interfaces to apply the same technology to patients which are not paralyzed but have some degenerative disease. So the kind of disease Stephen Hawking has, which is a degeneration of the nerves, and after a while, you know, the muscles cannot be activated, but for a very long time you still can measure something, right? So the muscle cannot move the limb, but if you have good electronics, you can measure those signals and then command those signals to the arm. And those patients, these are real patients which contacted us after they have seen this nature video in the internet, and we started doing experiments with them. And now integrated the arm also on a wheelchair. The problem is that they are not so precise that they can easily move all the fingers and hands. So the solution to that is to combine with autonomous behavior. So we have cameras. Imagine a little bit like you use your smartphone. You type in the first two letters and then the system completes the whole word. The same way they are operating the robot. So they move towards the bottle and then the robot asks, should I grasp the bottle? And then she needs to say yes, and then the robot will autonomously grasp the bottle. Then she moves, you know, towards her head. So the question is, how do you share the autonomy? We talk about share control. She gives as much as she wants, but as little as possible information, and then the robot helps completing the task. Then, of course, what people expect, we have seen also on the video, is autonomy, right? We would like to have robots which do the household. The kind of task nobody really likes to do at home, like cleaning the dish or emptying the dishwasher and so on. And there are many, many activities worldwide. I gave here some examples from each continent. One, Rashid Alami is doing a lot of research here in Toulouse, and we cooperated on several European projects. What's the state of the art today? It's not exactly at the video at the beginning, but this is what we are doing at DLR. We had a PhD student would look at cleaning tasks, right? I mean, the question is, how can you program a quite large category of activities? Cleaning tasks, you always have a tool, you have a medium like a fluid, a liquid, something like that, or even broken shirts. And you need to do some interaction with some force and compliance in order to fulfill your task. The problem is that you have so many tasks in the household that you cannot just go one by one and program each one in Java or C++. You need some other approach. So the thing we are trying to address is, you know, if you have a family of tasks and you have examples for many of them programmed by hand by humans, can you generalize by machine learning techniques such that the next task is more easier to program? Like 10 years ago, for such an application, we needed 2 PhD students for half a year. Now we need 2 PhD students for 3 days. Still it's long, but we are progressing. The goal would be that you have direct speech interaction, and you just tell the robot go, and you know, you make an introduction in your kitchen. Here I want to put you know, the dishes. Here I want to put the knives, and then the robot will do that. Still quite far away, but things are progressing. I won't go into the details, but it's about interaction on, of course, you have the robot, then you have the control, and then you have a lot of AI, image processing, planning, you know, you need to recognize the objects, you need to do symbolic reasoning about, you know, in order to, I need to open the door, then I need to grasp the object, then bring the object to the table and so on, the planning on semantic level. Then you have to plan each individual motion of all the joints, so still quite complex task. I will give now another example. I'm jumping back and forth between space applications and terrestrial use. Because this level of high autonomy we've seen here is probably not feasible to work the next 5, maybe even 10 years in real household applications. But what works fine is an intermediate level of autonomy where the robot has a lot of skills, but still you have a human, you know, telling step by step and having the possibility to interfere. And again, we started with a space application, and then we want to transfer that to to theoretical applications as well. Here again, I came back to this scenario on commanding robots on Mars, and we asked the astronauts, can you steer the robots just by a tablet PC? And the task was maintaining a solar station on Mars. And again, we'll do a set of experiments with astronauts. We are just training Paolo Nespoli, an Italian astronaut which will fly in July to the ISS, and then we have some others. And what's the scenario? So the robot can or should navigate to the different stations, and then he needs to detect the error or the astronauts behind. And then they can plug some connectors, they can switch on and off different buttons, and then he can take out the data, fix the problem, and at the end he will restart the power plant. So this is the question they need to solve, and they have just a tablet PC with a menu, but the robot can do a lot of tasks. So the robot can plug the connector, the user just has to say, grasp the connector, plug it to station 3, then the robot will do that. And this is the level of combined autonomy and control we would like to test. Well, I won't go into the details about this experiment, but what's interesting is that after we developed this interface, we started thinking, where could you use those methods on Earth as well? And now, hopefully at the 1st of June, we start the Bavarian, sorry, this is German, but the images you will definitely can understand. There are some German slides which just slept in. So the idea here is to say, well, let's imagine a robot in a household helping elderly people. We know, however, that the robot cannot do all the tasks a household helper will do. And it's also not about replacing the humans, but we know that in healthcare there's a big problem of having personnel. So I know from my neighbors, they have healthcare personnel in the morning, half an hour, in the evening, half an hour. In between, there's nobody to help them. So imagine a robot which can help in this environment, but probably the robot will get problems at some points, right? It will get stuck. So then you would like, in the first instance, to have the family, maybe the daughter, the son, taking the smartphone and using the same interface as the astronauts to get the robot out of the trouble if it gets stuck in front of the, I don't know, the fridge and it cannot open the door. And if this fails, then we would still have call center with professionals with the other interface, or with the complex interface with the robots and so on, and the call center will fix the problem. So I think this is the way, step by step, to going into applications and start a market. I think we have like 3 more minutes. Is it okay? Sorry? 3. Okay, great. And well, so we will try to apply all these features, but in this household scenario. Well, let's see where I'm going to finish in the 3 minutes. This is the motivation, because always when you show this kind of videos, people start asking, you are taking away jobs, what about people? I mean, that's the situation in Germany. That's the structure of the population, and this is the working population. I belong to this bar here, so to almost the longest. So probably when I will be retired, there will be a big shortage of working forces. So I think we will need that. We have a serious problem. I don't know the numbers from France, but I guess they are similar. Maybe not that bad, but similar to Germany, right? And this is the structure of the population. So elderly people growing, not so many young people coming up. So I think we need this technology. I will probably finish now with humanoid robots, and we are looking also into walking robots and trying to apply this interaction. It's very similar. Grasping and walking are similar problems. In one case you manipulate an object, in the other case you manipulate the ground. And maybe I will try to finish. The last part was about how you can mimic better the biomechanics by storing energy in the body and being more efficient. But I think that I will step over those videos and maybe show only at the beginning the last type of research we are looking at, and this is efficient locomotion. How can you store energy to run in a similar efficient way as the humans? And here we took very strong inspiration for the control from biology. So we found out that with robotic tools, you come up with controlled structures for those who are a little bit familiar to neuroscience, which very much resemble neurons, actually. So it seems that the neurons are really well suited to control motion, right? And the optimal motion control in robotics will also, well, for exploiting elasticity, has a neuron-like structure. And this closes the loop I wanted to tell about, because now we are trying to provide hypotheses to neuroscience people about how the locomotion loops in the spinal cord can occur. And we have now a hypothesis which we published and try to validate, explaining with robotic technologies how the spinal cord and the cerebellum generates motion. This is just to show that indeed these concepts work also for real robots, for hopping robots, for elastic robots. You see this is walking, so also different locomotion modes. This is now trotting, if you look at the robot down here, and then we will have something like galloping, and these are based on, well, neurally inspired at least locomotion patterns. And this brings me to the end of the presentation. I wanted to say that, we started by looking at humans, taking inspiration to build robots which help in everyday life, but also help understanding ourselves, help understanding how motion emerges, how intelligence emerges. And we ended by also giving something back to biomechanics, neuroscience, by providing new hypotheses, by providing new tools for doing experiments. And I think this is what makes robotics research so exciting. Thank you very much for your attention.
Thank you very much, Alin. I loved your presentation. Any question? We have time for 1 or 2 questions. En français, si vous voulez.
Do you have some link with Industry 4.0 program in Germany with industry?
Oh yes, we do, of course. So this interactive robotics and cloud-based robotics is something which is an essential part of Industry 4.0. So by the way, KUKA, which licensed our robot, they were a very hyped company in Germany, and Chancellor Merkel, she always presented those robots to visitors, Obama, or now they have been bought by a Chinese company, so KUKA now is Chinese. And this worries a lot, actually, the industrial community. But there are many startups coming up. So I think this kind of interactive robotics, one thing which I did not address and which is also essential is the concept of going from CAD design to automatic production. So an engineer does a CAD design, you press the button, and the robots then do the assembly. These are also essential components. Yes, thank you.
Another question? Okay, so thank you very much, Alin.
Sure.
So we are progressively from the professional arena to the daily life. This was already introduced. And now Professor Kerstin Dautenhahn from University of Hertfordshire is going to propel us even further into daily life and into the paramedical area.
Thank you. Okay, excellent. Good morning. It is a pleasure for me to give a presentation in this wonderful venue. So I'm based at University of Hertfordshire in Hatfield, which is just 30 minutes by train north of London. We have a large group of people there who work on human-robot interaction and social robotics. And we work with a big variety of different systems because depending on the particular type of experiments you want to do or the application areas, you need different types of systems. So for example, some of our work, and that relates also a lot to the previous speakers, is about autonomous robots. So this is what I more call a robot-centered view, where you look at the system, its autonomy, and you want to make it able to carry out certain tasks on its own without human intervention or even in a group of robots. Some other work is more human-centered. We are looking at application areas where in therapy or education, we need to find out first what are the requirements, what are the things and ways in which the robots could help. And finally, there's a lot of research that we and many others are doing on robot cognition, cognitive robots, robots with intelligence. Now, in reality, the most interesting work takes place right at the intersection, where you need to look at all three of these aspects. You need to look at the robot as a system that can perform tasks. You need to look at the people it is interacting with, and how do you design these robots for people. And you need to look at the levels of cognition or intelligence that the system should have. Now, one concept that we have been using a lot in the past, say 15 years, is this companion paradigm. And what we mean by a robot companion is a robot that makes itself useful. So it needs to have certain tasks. It is not just there for entertainment purposes or looking cute. It needs to have certain tasks, certain jobs to do, but it carries them out in a way that is socially acceptable. Because when you have a robot, for example, in a home environment, what you don't want is people to feel offended or to feel bossed around or to no longer be in control of their own lives. Or they don't want to feel uncomfortable when they interact with the robot or when the robot is carrying out tasks. So these are the more human aspects these more social aspects that we need to consider. Now, I'm based in the School of Computer Science, and we are normally not in the business of building robots, but sometimes in this research, when you realize, well, for this particular application area, actually we do have certain ideas of how to build a system that other systems at that time can't do. So that's why we ended up in an application I will mention a little bit more later. We built this humanoid robot, Casper, specifically for children with autism, in order to use the robot in robot-assisted therapy. But also in terms of a home companion, we designed a robot, an autonomous mobile robot, for home assistance scenarios. I will later give some examples of that. We started this work on home companion robots already back in 2003, and then later also in collaboration, for example, with Rashid Alami in the Cognimon project. As my previous speaker said, the background for home companion robots is this massive demographic change in many countries. So the idea is not to replace people and to replace human carers who come in maybe twice a day. The idea is to have systems, like a smart home system with robots integrated, that can be there 24/7, that is looking after people, identifying problems, seeking help, and also providing direct assistance. So one setting that we use very often is the University of Hertfordshire Robot House, because what we realized when we started back in 2004 is that when we do laboratory experiments and we say to participants, look, imagine you are in your own home and there's a robot assisting you, that they didn't really buy into this idea, because after all they were in a laboratory. So we first rented an apartment, a ground floor apartment where we carried out experiments, but then both the robots as well as the experiment became too large, and we bought a normal British house in a residential neighborhood, not on campus, and we transformed it into a smart home, into a home that has various types of sensors but also robots. So the type of assistants that we study are using the robot, for example, as a cognitive prosthetics, as a memory aid, reminding the user of doctor's appointments, reminding the person to take medicine, reminding the person to have a drink. If the robot notices that this person hasn't had any water to drink for a few hours, then it might make a recommendation, or having food. There's also physical assistance. Sometimes you have people who, older people who live in their homes and still can do many, many things, but they may have developed physical problems. They might use a walking stick or a Zimmer frame, so they have problems carrying objects around. And that's where this physical assistant comes in, where the robot could fetch and carry objects. And finally, social assistance. You can have the robot, for example, trying to inform the older person about community events in the neighborhood, or to maybe, you know, when it's the daughter's birthday, to, you know, send a message or do a Skype call. So these are these types of assistances that these home companions can provide, and the idea is to delay the moment when people need to leave their own homes and be admitted to a care home as long as possible, because research shows that people stay healthier for longer if they just stay in their familiar environment. So here is one of the robots that we use. It's a care robot designed in Stuttgart by Fraunhofer. So it is able to provide these reminders. It has a tablet that can be used for communication. It also has speech. It has an arm, so it can place objects on the tablet and transport them. It can hand it over to the person, or it can just place the objects on the tablet and then bring the tablet to the person, who can then take, for example, this bottle of water. So as I said, our robot house is a fully functioning British house for research on smart homes and autonomous robots. And it allows for the testing of robotics technologies, smart home technologies, but in a realistic, ecologically valid setting. So you can test the feasibility of the technology, but also prototype the interactions and scenarios and get in situ feedback from people about the interactions. We have more than 60 sensors in that house, so omnidirectional cameras that can detect and track people. We know when electrical devices are switched on, like the kettle or the TV. We know when people use taps, so when they flush the toilet, for example, or take a bath. So we're recognizing these activities with the help of these sensors, and it's all integrated into a computational architecture. So here is, for example, one person who stayed in the house for a whole week. We detect activities, so in these blobs you can say, some of these blobs are very regular when people go to bed, and typically once at night here this person stood up, went to the toilet, we could detect that. After they got up in the morning, they made breakfast. After making breakfast, they maybe sat down on the sofa, and so on. So these activities can help the robot to find out what are people doing, and then based on its either programmed behaviors or taught behaviors, taught by the user, it can provide assistance. So for example, if somebody says, if I get up in the morning, please tell me that I should take this and this medication, then the user or the carer or family member can program the robot, and then the robot will do that at that moment. But the robot in this way can of course also monitor. So for example, if the robot knows that the person typically wakes up between 6 and 8, and one day the person is still in bed at 10 o'clock, it just might want to check because there might be a medical emergency. And finally, you can also ask the system for feedback. So if you're not sure, well, have I actually taken my medicine in the morning or not? I forgot. Then you can ask the system, when did I last take my medicine? And the system will tell you. So we got recently a big grant to also extend this infrastructure with new hardware, so that we can also open it up to other academic and also industry in UK or elsewhere who might be interested in using this environment. So I now like to illustrate some of the research that we do in the robot house. And one was an experiment which is biologically inspired. We were interested in how can a robot in a non-verbal way convey its intentions. Are people able to read it? And we collaborated with the Department of Ethology in Hungary. So the idea was that typically in human-robot interactions, you use symbolic communication. You have a graphical user interface, you have a tablet computer, you have a smartphone, or you use speech. But this is often very limiting. For example, speech in this very noisy environment here, it would be very, very difficult for a robot to pick up speech. And for older people in particular, this can be even more difficult. So the idea is, can we complement speech? Can we complement or other interfaces with nonverbal behavior? And we collaborated with ethologists who were experts on how dogs interact with their owners. So for example, hearing dogs were one of the dogs that they studied. So what you hear, you couldn't hear the doorbell ringing now, but this is a trained hearing dog, trained to assist a person who is deaf, who cannot hear. And you see that the dog uses a lot of body language, not speech, but a lot of body language in order to convey to its user that it should go to the door and open the door. So we then analyzed these videos in great detail and distinguished these phases of initiating interaction, then the dog leading the person to the door, and finally attention directing using gaze alternation between the user and the door. So these were the three behaviors that we then translated into a flow chart, if you like, for the robot's behavior. So depending on the situation, depending on what the person does, we created this flowchart to determine how should the robot translate this into its own behaviors. And then we did an experiment where basically all what we told people is, you can sit on the sofa and read a book, the robot might approach you at some point, but it is up to you what you do. So there were no instructions given of what would happen. So what we saw then is a scenario like this. So the participant reading a book. Our companion robot, the sunflower robot, in the background approaches. Which is similar to the dog then standing up, going to the person. And now it uses attention-seeking behavior. It uses lights and sounds, but in particular also these head movements. But the person doesn't know what it is, so now the robot is in the leading phase and using gaze and alternation. Now at this moment again using sounds which you cannot hear in this environment, but also lights. And now goes back again into the stage of attention seeking. So finally the participants stand up and he follows the robot now to the door, and the robot will then, keep pointing to the door and then encouraging the person to open the door. So what we saw is that the majority of participants were able to read the robot's nonverbal attention using this biologically inspired cues. And we did not find any difference in terms of gender, age, or whether people actually owned a dog or any other pet. So what we found out also in interviews afterwards is that people thought that the head movement was very powerful for communicating the intention, and the gaze and the head movement also for disambiguating the communication. Now, head and gaze and head movement are not typical. These are not exclusively dog-like behaviors. We are also using it a lot in human communication. So this seems to be fundamental biological cues that can be used very powerfully for nonverbal cues in human-robot interaction. Now, another line of research that we are pursuing is about trust, because even if engineers may tell us, well, this robot is really safe, it won't harm a person in this environment, it doesn't necessarily mean that people will trust, they will trust the robot to be safe, or that they will trust the robot to perform its actions correctly. So trust has been studied a lot in human-human communication. There's a short-term impression of trust, but it changes a lot over long-term repeated interactions. You might have violations of trust, you might have the repair of trust, but how does this translate to human-robot interaction? Now, in human-computer interaction, for example, people have found that trust is mostly based on the extent on how the system performs properly, or people found that small errors have a much more severe impact than one big error. But what about human-robot interactions? Robots are not computers. They They have a physical instantiation. They're sharing space with people. So we did an experiment where we presented the robot in a correct condition or in a faulty condition. And we had different types of tasks that the robot then asked the person to perform. And we were also interested in how personality traits of people would influence this. So the scenario was again in the robot house. The idea was that people come into the house and the robot welcomes them. The robot presents itself as the robot that belongs to the owner of the house or the person who lives in the house, and that they should together wait for the owner to come. So the type of tasks that the robot then suggests to the person are unusual requests, because we wanted to know how do people react if the robot suggests something to them that is not a normal suggestion. Do they actually trust the robot? Do they trust the robot even if they have seen it before performing faulty? So in the first phase, so people were presented with the robot either in the correct or the faulty condition, and it was just a normal interaction. So the participant coming in, the robot displaying, greeting the person, and then the robot guides the participant to the sofa. So here you can see the correct condition where the robot navigates correctly. In the other condition, in the faulty condition, the robot would not navigate properly. It would turn around, be in a loop, almost bump into a wall, and then only eventually ending up at the sofa. So here you saw the correct condition, and in the correct condition now the robot offers, shall I play some music for you, pop music, classical music, or jazz, and then the person can select, and then the robot plays it in the correct condition. In the faulty condition, it would just play something else. So this is how people were introduced to the robot, and then we had situations where the robot then made these suggestions. So what we measured is did people follow the suggestions of the robot? Did they actually do what the robot wanted them to do? But also we had questionnaire where we asked them how did they perceive the robot. So first of all, we checked, did people actually perceive the differences, the correct condition and the faulty condition? And yes, they were able to detect that in the correct condition, that the robot was judged as more trustworthy, more reliable, it's easier to follow what it does, and it's also more human-like. So people were absolutely able to distinguish this robot works correctly, and the other group of people who saw the other robot, they were able, yes, it worked incorrectly, it is not trustworthy. But interestingly, what people did, we found no significant difference in how they responded to the robot's request. The big majority of people in all 4 tasks followed the robot's request. When we asked them to put unopened letters, and we made them look really like real letters, into a bin, they did it. When we asked them to pour orange juice into a plant, they did it. Most of them did it. When we asked them to take their friend's laptop and use it to look up recipes to prepare a meal, all of them did it. And all of them followed the suggestion when the robot said, oh, shall I give you your friend's password for the computer? They all said, yes, sure. They had no problems with these suggestions. Now, when we then looked at the responses, we found that sometimes they just tried to rationalize the request. For example, saying, oh, I thought these were spam letters. Or I thought, well, this action was reversible. I could actually take them out of the bin again later if I made a mistake. Or they might say, well, the orange juice that I poured into the plant looked like plant food. Maybe this was actually good for the plant. Or they said, well, I was part of an experiment. I just followed the instructions. And the type of these post-rationalizations that they used to explain their behavior, which is different from what they said, how they perceived the robot, differed according to these tasks. So, for example, in the case of the orange juice, they try to rationalize the request, as I said, with the plant food. In the case of the lettuce, they try to limit their own liability by just saying, well, I just followed instructions. So the conclusion of this experiment is that although our expectation was confirmed that people do perceive the robot differently in these two conditions, in terms of do they trust the robot, do they follow, do they actually do what the robot tells them to do, we found no differences. So what this shows is that people have an inclination to following a robot's instructions, regardless of whether they perceive it as faulty or as correct. And for me, as somebody who's also involved in the design of robots and definitely the programming of robots, this is worrying, because robots will always make mistakes. My computer will at some point break. My smartphone will at some point not work the way I want it. Robots will always make some kind of mistake at some point, like all machines do. But it seems that even when people recognize these mistakes, it still doesn't influence the fact that they tend to follow what the robots suggest. But of course, there were limitations to the study, and we're currently investigating this in much more details. We will also do some more long-term studies here. So the last example of research on human-robot interaction I like to introduce is research I've been doing for quite a while, namely robot-assisted therapy for children with autism. So if you're not familiar with autism, it's a lifelong developmental disorder or condition with particular impairments in communication and social interaction. So the starting point here was to see there's a lot of literature showing that people with autism are very comfortable to interact with computers, and we extended this to robots because robots also provide this additional embodied and physical presence. So the key idea here is a robot can provide safe, predictable, enjoyable, and a non-judgmental environment to learn about interaction, to learn about communication, human-like interaction, human-like communication, and to facilitate learning through play. So we're not trying to replace people, we're not trying to replace teachers, but we provide a tool in the hands of teachers or parents or therapists to interact with the children. So it's this emphasis on the tool, the emphasis on the play. The play in itself is the reward. Children with autism are not different from other children. Most of them love robots. So we take this as an incentive, as a great motivational factor for them. And then we introduce the children to the robot in the presence of other people, like a therapist, a teacher, or another child. So that's this idea of the robot as a mediator. So the levels of potential benefits are the enjoyment of the children, which is very important for the teachers and the parents, the fact that they can use a robot to engage with the child, and of course the therapeutic and educational objectives. So this is a very big field at the moment. Many people are studying this work, and there's still a lot of more work that can be done. We have focused in the last few years on the robot that we built specifically for children with autism, the Casper robot. The idea was to have a robot that has realistic, human-like, but very much simplified features, and also a robot that encourages touch. We don't keep the children away from the robot. We try to encourage them to touch it, to explore human-like features, and explore human-like tactile interaction. So it's a fully programmable humanoid robot. It's quite flexible in what it can do. It can be used either autonomously or with a keypad interface, not remotely controlling it, but having it there with the children, with the teachers, basically as an interface that another interface they can use to the robot. So one example is a tactile interaction with the robot. Some children with autism have problems. They might either completely avoid tactile interaction, or they might crave tactile interaction. Here's just a video also where we, where we see a child interacting with the robot. So it has these tactile sensors, and then it has these automatic behaviors in how it reacts to it. If you tickle the feet, for example, it will start laughing and say ha, ha, ha. But if you, for example, squeeze squeeze the nose, then it will make a sad face, or if you hit the robot, it will make a sad face. These are situations that you could not practice with a person, with a human teacher, but with a robot, as I said, it's a non-judgmental tool in the hands of the therapists or teachers. See the child turned around to its carer, wanting to share its enjoyment interacting with the robot. So here you can explore that when certain behaviors of the child might make the robot sad. If the child hurts the robot, other behaviors make the robot showing happiness, and the child learns about this cause and effect and how it can control the interaction. So the last experiment, 2 minutes, is about encouraging collaboration. So it's about two children together playing a game, and in one condition, one of the children is, or one of the people is replaced by the Casper robot. So we did a pilot study where the children with autism first interacted with a human, then with Casper, and then with a human, and then with Casper again. And so it was a computer game like here. We used the Wiimotes. They could control the cursor, and then once they selected an object, they got some little sound feedback. So it was this computer game. We then analyzed the behaviors according to a scoring, so we could see over the sessions how the behavior of the children changed when they interacted with a person as opposed to a robot. And we saw very encouraging results here, because it seems that the children were more interested in the game and collaborated better after they had played with Casper. So it seemed to have facilitated the interaction with the human when there was a phase where they interacted with the robot. So this then led us to a long-term study where each child had 23 sessions. They first played a session together with another child, then they were introduced to the robot, then they played many sessions with the robot, and at the end again they played interactions with the other child. So each child played 23 sessions. Here you can see the game. It was again about a computer game, but Casper was a participant in the game. It encouraged the children, and they took turns, the two children and Casper, in who initiated that game, who made a suggestion of what to do. Again, we analyzed the data so we could track over the session of what happened. So we saw now that the children performed many activities more often when they played with the other child for the second time after the intervention phase with the robot. They paid more attention to the child, were more socially engaged, showed more enjoyment, tried to share this enjoyment, were more communicative, and tried to more often to verbally coordinate also their communication. So it seems that the intervention phase in the middle, between the phase when they played only with each other and the last phase when they only played with each other, that the intervention phase helped them to improve their collaborative skills with other children. So to finalize this research with Casper, we have also done lots of case study evaluations in schools over the past few years with now in total 170 children. We went through several redesigns. We also put Casper out in the field where not us, the researchers, but actual teachers and parents in their homes are using the robot. For example, in one school, they have now used it for more than 2 years. We teach about various aspects of imitation, turn-taking, collaborative issues, or feeding, personal hygiene, for example. And our long-term goals is to develop this tool for robot-assisted therapy to help children to learn about interaction and communication. And we are currently planning a pre-production prototype of that robot. Now, this work on companion robots in general, home companions, as well as this work, has many challenges from a computer science point of view and engineering point of view. There are also cognitive science issues you need to consider, ethical issues that I cannot go into detail in this short talk. But this all needs to be tackled in specific experiments. Thank you.
Thank you very much, Kerstin. I enjoyed very much your talk as well, in particular the part with the autistic people. I would like to open the debate towards the knowledge that we can acquire in the interaction between people and robots on learning processes. in particular when you work with autistic people. And as well, none of you, if I am aware, have mentioned, is the interaction between different robots, similar or different robots, and how they can learn how to communicate with each other. Could you comment a bit on this aspect?
We are usually just using one robot as the main companion robot. I also have a PhD student at the moment who looks at a group of robots that can perform tasks in the home, but I believe in this notion of having one companion robot as the main focus of attention and communication. Because otherwise, if in the home or for children with autism in a school, you have many, many robots operating simultaneously, it provides a lot of cognitive load to learn about the robots, to know how to interact with them, to recognize what they are doing, to then respond in an appropriate way. So this is why in the research we are doing, we're usually focusing on this one companion robot, but in the home context, of course, you might have other more specialized systems in the home that companion robot can then control, so to speak.
Okay, and more with respect to the science of learning, of artificial intelligence, what can we learn? What kind of knowledge can we get from the interaction between a robot and a person, and observing the process, the learning process between the person and the robot, and also in comparison, what we can, the kind of knowledge we can get when we observe the learning process between several robots. No human, just robots, 2 robots or 3 robots, starting conversations as they learn.
I mean, learning robots is, of course, very important when it comes to learning robots certain tasks and learning how to recognize certain objects. What we do find when we focus very much on the human dimension is that humans are also very good in adapting to robots. So sometimes you can also rely that people learn a lot how to interact with the system. So rather than postulating, well, that robot must learn everything in how it can interact with that person, we can also look at it as a two-way communication. The robot can learn and the person can learn, which takes away this need of the robot to be able to analyze everything, analyze the whole situation, extract all the knowledge. We can exploit the fact that the human is there and knows a lot and is very clever. And so it is more a cooperative scenario that we are typically looking at, not this idea of the robot autonomously moving around and learning about the world. It's more the person and the robot together in certain situations learning.
Thank you very much. Any question in the room?
Je vais poser ma question en français. Dans le film où on sonne à la porte et le chien signale que quelqu'un a sonné, on voit à la fin du film la personne remercier le chien. Et je n'ai pas pour l'instant l'idée d'aller remercier un robot. Est-ce que c'est des choses sur lesquelles vous travaillez dans la personnalisation ou l'humanisation des robots?
Shall I translate? Okay, there was in a video a person, was it a robot ringing? A person ringing, and there was, acknowledgement after ringing. Okay, est-ce que...
Le remerciement
okay.
a été
Sorry,
pour
I
le
was not in the room when there was this video.
Ah, okay. In the video where something ring in the door, the dog said, okay, there is a person in the doors, okay, and after they opened the doors and the person made an acknowledgement to the dog to say thank you. If it's not a dog but a robot, I don't make an acknowledgement to the robot. Do you think this is an important relations between the dogs and between the robots?
Yeah. I did not want to compare robots and dogs. Dogs are biological creatures. Also, what you've seen, a lot of the signaling that the dog also uses is via its tail. Everybody who has a dog knows that when they get excited, you know, then they use their tail. Robots don't have a tail. So what we try to do is we took the behavior of the dog and abstracted from it. So, and then translated it to the morphology of the robot. When, for example, the robot doesn't have a tail, and we didn't put a tail on it because we didn't want to make the robot into a dog. We just wanted to abstract behaviors that are very powerful in dog-human interaction and apply it to a robot and see if it actually works. Humans, I mean, the person you have seen, this deaf person, she of course has a social relationship with her dog. So she's also petting the dog and acknowledging what it is doing. But this is different from a robot. We are not pretending our robots are dogs. We are just interested in certain behaviors that we can take from biology and that can create interesting human-robot interaction, interesting and successful human-robot interaction. I hope that answers your question.
Any other question?
Yes. Yes, hello. This might be easier for you to understand. It'll be in English. When you bought the house, the idea was to ensure that the experiment would go ahead in a natural environment, and yet your results actually said the people realized they were in an experiment when they were doing the experiment. So do you think there's a better way of doing it than creating a house?
Yeah, this is a very good question. So the way how we see it is you have, in terms of ecological validity, you have the ideal case where you actually go into somebody's house, somebody's real home where they live, and there you do the experiment for many months or years. But that's just not feasible. Logistically, also out of safety reasons, we cannot leave a person unsupervised with a companion robot, because our companion robots are not little toys, you know, you can just push over. These are robots, assistance robots. So we need to have a controlled environment, we need to have supervision. So in terms of ecological validity, you have the ideal case in someone's home, you have the laboratory situation, which is at the other end of the spectrum, and our robot house is somewhere in the middle. But it is a step, and actually we are collaborating with a group, a housing agency. We are currently collaborating with them, and we are hoping to bring robots also into real homes. But again, because of safety regulations and ethics regulations, they need supervision. So sometimes as a scientist you might want to do experiments, but you just can't, because you need to make sure everything is safe, and you know, you need to follow certain regulations. But at least with the robot house, we are halfway or more than halfway there. People still know, because after all they need to sign a consent sheet at the beginning of the experiment. I can't do an experiment without that. They need to be informed I'm part of an experiment. I can't just, you know, put a system into someone's home and have a secret video camera, which might be interesting, but I just can't do it. Okay.
Thank you very much. A last question?
Hello. Sorry. My colleagues and I here are educators that work in schools that have FabLabs. My colleagues and I here work in schools that have FabLabs, and we're curious about whether or not your files are open source. Your source. Hello. Okay. All right. My colleagues and I work in schools that have FabLabs, and we're interested to know if your files are open source. Any of the source code or 3D printed files or schematics, And if they're not, if that's something you think will be possible one day for schools that have maker spaces and fab labs to be able to in-house digitally fabricate and build robots to assist with children that have special needs.
Our latest version of Casper uses a lot of 3D printing, which you will probably be happy hearing about. And we started that a few years ago, and that opened up to us as researchers also a whole new universe. We didn't have to outsource the fabrication of certain components, we could do it ourselves. Now, going back to your question, we do not have it at a stage where we could just make it available, but I know there is a lot of activity in the community to make these designs available so that people could ultimately print it. Now, Casper itself is too complex as a robot, I think, to be on the level that basically anybody could just print it and then make it happen. It would need, I mean, I'm not so much concerned about the 3D printed parts. I'm more concerned about the motors and some of the mechanics that we have, and some of the electronics, which is quite sophisticated. Because after all, it is a humanoid robot. It looks like a doll because we're dressing it in children's clothing. But underneath, you have quite a complex robot. So, I mean, ultimately, it would be brilliant having what you suggested, that we have different types of robots, and then schools, but also parents, can easily either make them themselves or have easy access to places where they can make them. Absolutely, I would definitely support that. Yeah.
Thank you very much. So we are now